Hi, I'm Asadat Sabari from the Technion, Israel Institute of Technology. I will present to you a new method developed by Yoav Shechner and myself, called the Polarized Optical-Flow Gyroscope. Polarization is used by a wide range of animals for navigation. Some of these animals have very crude spatial resolution vision and very small brains. In other words, their vision resources are limited. However, observing the sky or underwater polarization patterns, even in poor resolution, yields a strong navigational cue, known as the polarization compass. This polarization compass is used in bio-inspired robot navigation, relying mainly on celestial or underwater polarization patterns. These systems can use low resources and reduce dependency on GPS and inertial measurement units. This is our inspiration as well. In this video, I will answer two basic questions. 1. What is the Polarized Optical-Flow Gyroscope? And 2. What is the added value? Let's start with our first question. Let's say we want to assess the rotation of this camera. Optical flow is governed by the brightness constancy equation, which demands that change in intensity be caused solely by motion. It exploits temporal intensity changes caused by motion of high contrast spatial features. It is an image-based method. Optimization of the brightness constancy results in a vector field of velocity, the optical flow. Featureless regions, like the sky here, do not contribute to this classic method. In rotation, the center of rotation is also not informative. Therefore, the velocity in such regions will not be estimated correctly. But let's rigidly attach a simple polarizing filter to the camera. Then eager rotation induces readout changes. In this case, the viewed light intensity is a function of the object intensity, denoted here as C, the degree of polarization, P, and the angle of polarization, theta. In eager rotation, the polarization angle of incoming light changes relative to the polarizer, resulting in readout changes. We unify these principles by generalizing the brightness constancy equation. As in the brightness constancy, we may demand that change in object intensity and degree of polarization be caused solely by motion. The relative angle of polarization is a different story. Let's say this camera is rigidly attached to a polarizer. Let's simulate translational movement relative to this pencil, which has an angle of polarization marked by a yellow arrow. The relative angle of polarization of the object does not change by translation, only the position of the object in the frame. There's constancy. However, in rotation, the relative angle changes opposite to the rotation. We use this to generalize the brightness constancy and yield a polarized optical flow equation. In this equation, regions having partial polarization contribute to motion estimation, as well as spatial features which have significance in optical flow. We put this to use in passive sensing of camera eager rotation. We constructed the setup in which a linear polarization filter was placed in front of a camera using a mounted protractor. Both camera and filter were rigidly connected to a rotating stage, having its own protractor, allowing controlled rotation. We found the rotation may be estimated and therefore traced by optimization of the polarized optical flow equation. In other words, we created a gyroscope. So to our question, what is a polarized optical flow gyroscope? A polarized optical flow gyroscope is a method for rotation estimation. It requires attaching a polarizing filter to the camera and applying optimization of the polarized optical flow equation to the camera readout. Now let's move on to our second question. What is the added value of this method? First, let's look at some results. We show here the most basic scene for polarization, a clear sky viewed by cameras with and without a polarizing filter. The images are not in true color. You see here the intensity in jet color map. You can see that the intensity viewed through a polarizer is much lower than without. We rotate both cameras by 6 degrees. You can see that without a polarizer, there's hardly any visible change in the readout. Both Hornschunck and Lucas-Canada optical flow could not retrieve the correct motion. The polarized optical flow gyro, on the other hand, estimated within a 5% accuracy. But is the success confined to such specific scenes? To answer this, we also tested our gyro method on a variety of scenes, both simulated and experimental. You can see here the light intensity of these scenes. This is what the polarization of the scenes look like in hue and saturation representation. As you can see in the color wheel, the hue represents the angle of polarization, while the saturation represents the degree of polarization. The different scenes represent different possible scenarios: high polarization, low polarization, high features, and smooth scenes. For each scene, a series of different rotation angles was applied, and then each estimated individually. The error, as you can see, is less than 1 degree for rotation of less than 15 degrees, and less than 3 degrees for large angle rotations. We must ask, to what extent is this result due to polarization? To answer this question, we must compare the sensitivity of image-based analysis of rotation and the sensitivity of the polarization compass. Let's start with the image-based analysis. Let's define R as the distance between a random pair of edgelet pixels. Its length is typically half of that of the frame. Rotation means that the interpixel vector tilts slightly within a time step of delta t. Since the basic resolution of this vector tilt is a single pixel, the edgelet pair can resolve a rotation rate given by the ratio of the arc length of the pixel motion to the time step of the motion. For the full uncertainty, we take into account the total contribution of all edgelet pairs. Now, let's examine the sensitivity of the polarization compass. Let's deal with polarimetry in spatially uniform regions. Due to rotation during delta t, the intensity of a pixel changes uniformly within a region. Delta I is the resolvable intensity of the pixel. For the full uncertainty, we take into account the total contribution of all segments. We compare the image-based uncertainty of rotation estimation and the polarization compass uncertainty. The relation depends on the polarization and measure of structure and the width of the pixels, L. The polarization has obvious circumstances of added value, such as smooth scenes with high polarization and single or large pixel imagers. Image-based analysis is obviously more valuable in high-structure scenes. However, we see here that polarization may have significant contribution even in structured scenes. In other words, we may say that the polarization compass is generalized here to structured scenes. So to our question, what is the added value of this method? The beauty of polarized optical flow is in that it unifies image-based analysis and polarization compass in a single method. In scenes with high structure, optical flow will be more dominant. In smoother scenes, polarization will be more useful. However, most scenes will profit from both. The qualities of the scene do not need to be known prior to the use of this method. In practice, this approach can be useful in low-resource outdoor navigation, having the sky in view or underwater. Polarization-based navigation aids assume models of the expected polarization pattern. This paper shows that the rotation rate can be derived in unknown scenes. In addition, this rotation cue can assist self-calibration of distant imagers, such as low-resource nanosatellites. Thank you for watching. We hope you enjoyed our video. For further information, we encourage you to read our full-length paper.